Today we're going to be talking about gas filter correlation NDIR or GFCIR for short. So to start, we're just going to draw out the analyzer. So first thing we need with this analyzer is a source. This is an incandescent bulb like we use for other IR instruments. So that's the source of the radiant energy. Next thing I'm going to draw here is a sample cell. The sample cell is where the sample flows through, as well as where you would introduce the zero gas and the span gas to calibrate the analyzer. And we also have a detector. So this is a non-specific IR detector that can detect a broad range of wavelengths of IR. The next thing we need to draw here that makes it the actual GFC, the gas filter correlation IR, is the gas filter. So this is a filter on a wheel, and the filter contains the gas we're analyzing and a reference gas that's usually nitrogen. So there's little chambers in this filter, and those contain a high concentration of these gases. So that's called the filter wheel, and I'll just draw another view of the filter wheel so you get an idea of what it would look like. So this would be looking at the filter wheel head on, and there's little cartridges in the filter wheel that are filled with the gas, the gases of interest. So we always fill these with, one gets filled with nitrogen, and that's actually how we do the measurement for this analyzer, and the other one gets filled with the gas we were trying to analyze. So next I'll do a little example to show you what we mean by gas we're measuring. So for the example, label where the gases would go if the GFCIR is set up to measure ethylene. So ethylene is the gas that we want to analyze. So here's our analyzer. In one of these gas filters, we always put nitrogen because that's actually how we obtain our data from this analysis, and I'll show you what I mean next. And the other filter has ethylene in it. So now we're just going to talk about, once we have our gases in there, we'll talk about how the signal is processed. So what does the signal look like from each of these gas filters when the analyzer alternates in between? So on the left side of the screen here, we're going to have zero gas in the sample cell. So on both the top and the bottom, zero gas goes into the sample cell. And we're going to draw the signal for what it looks like, the signal looks like when zero gas is in there. And over on the right side of the page, we're going to be talking about span gas. This could also be, it'll look similar for a sample gas as well. And then we'll draw in next where the position of our filter wheel is going to be. So on the top row of the page, we're going to draw the filter wheel. It's going to be filled with the gas we're measuring, the gas we're trying to analyze. So in the last example, that was ethylene. It's whatever gas we want to analyze. And on the bottom row, we're going to draw the filter, so the filter is open with nitrogen in the cell. So that's filled with nitrogen. So now we're going to draw the top left. So we have zero gas, and our measurement gas is in the screen, and we're going to draw the signal on the bottom. So the light comes out, hits the measurement gas filter, and most of that light gets absorbed by that high concentration of measurement gas. So not very much light is going to reach the filter. So we'll draw that, what that looks like on the graph. So that this is a graph of time versus transmittance, and there's very low transmittance. So we're drawing it down there. Next, the light's going to travel on the bottom through the nitrogen filter. It just travels through because nitrogen doesn't absorb IR. And then it travels through the sample cell. It's full of zero gas. Zero gas doesn't absorb the nitrogen, or doesn't absorb the light, so there's going to be high transmittance in that case. So we draw high transmittance on our time versus transmittance plot. And if we flip back, we start getting a step function with a very big amplitude. So that's for a zero gas, a very big amplitude. Then we're going to move over to our span gas. So the measurement gas, again, absorbs a lot of the light. Most of the light is absorbed, so if 99% of the light is going to be absorbed, very little gets absorbed by the span gas, and the signal looks about the same as it does on the left side of the page. So most of the light's absorbed by that measurement filter. When we look at the nitrogen filter, the light goes through the nitrogen filter as we expect for nitrogen, and then the span gas absorbs a lot of the light. So just some of the light makes it through the detector. So there's a pretty low transmittance, high absorbance for that. So if we draw on our plot, we have a pretty low transmittance. And if we start making a step function when we flip between filters, you're going to see a very small amplitude for the step function. So for this analyzer, as the concentration of the gas increases, the amplitude of the step function actually decreases, which is the opposite. This is called negative filtering.